Hello, class. Okay, so we did this problem with the diverging lens in class. And the number didn't make much sense, so I'm going to look over it again. So it was a problem where we have a van. I'll read the problem. So here's a person in the van. Okay, so see, the owner of a van installs a rear window lens that has a focal length of minus 30 centimeters. So it's a diverging lens. So it's in the back of the van. Okay. When the owner looks out through the lens at a person standing directly behind, so there's someone standing behind the van, we don't know exactly where. The person appears to be 24 centimeters so the image of the person is 24 centimeters. Okay, he's very tall. And appears to be 34 centimeters tall. So yeah, I'll make him a bit shorter. Okay, so the height of the image, that's how tall he appears to be. That's 34 centimeters. Okay, how far from the van is the person actually standing, and how tall is the person? So this is the image of the person. And again, we're given this distance is 24 centimeters. And let's look at our basic equations. Okay, so magnification, HI over HO, that equals minus DI over DO. And the thin lens equation. And remember, we have to use the sign convention for this as well. So, like when I first did this, I found the person to be extremely short, which, like the actual height was, less than the image even. So clearly something was wrong. So let's do this again. We want to use the equation. Let's start with that. We want to start out, we have DI, so we need to find DO. And we have HI as well. So, we have DI enough. We can just use this equation to find DO. Question is, we have to just be very careful with the sign convention. So let's start out. Let's move the 1 over DI to the other side. Okay, so DO DO is F times DI divided by DI minus F. So just flip each of these. But now again, we have to use the sign convention here. And the person is standing behind the lens. So normally when we do these lenses, we have the lens here, whichever converging or diverging, doesn't matter. We have an object here and an image over here. This time, the object, we're told, is behind the lens. So let me read the sign convention that we have from the book and the notes under thin lens equation. Here, let's look at, let's see, object distance. Or no, I think we want to find, Yeah, let's look at image distance. It says DI is negative for an image, or DI is positive for an image formed to the right of the lens by a real object. And so initially I had DI is positive. It says DI is positive for an image, real, formed to the right of the lens. But the next part of that sentence is by a real object. However, the object in this case is not real. A real object would occur on the left side. So because the object is on the other side, you have to reverse this. So DI in this case is actually negative. So yeah, this is the first problem we've dealt with where we had, again, the only time this normally comes up, or usually when this comes up, is when you have two lenses. There's an example in the book where you have two lenses. You have a converging lens and a diverging lens. So you use the image of the converging lens, which for the image, let's call this image 1. That forms to the right of the diverging lens. And so that is called a, we're using this as the object now. This is called a virtual object. And so, yeah, we have to be clear that that sign convention only applies to a real object. So we have to be a little more careful dealing with a virtual object. In this case, that means that DI is negative. That's like when you have the object and the image on the same side. We use a minus sign for the image. So, yeah, that was the problem. Let's continue with that. Yeah, I guess if you figure the object is over here and light shines this way, you'd get a virtual image with a negative sign. So, yeah, that image distance should be negative. This would be, yeah, basically this would be comparable to your lens here. Your object here. And say the image occurs on the same side as the object. If that occurs, then DI would be negative. And basically that's what we have over here, just looking at it from the other direction, because the object and image are on the same side. Okay, so now with that, the numbers should make a lot more sense. Okay, so DO, we can now plug in our numbers. We have the focal length, which is minus 30 centimeters, times minus 24 centimeters, divided by DI minus F. So that would be minus 24 minus negative 30, that would be 6 centimeters. 24 over 6 is 4. 4 times 30 is 120. Oh wait, yeah, positive 120. Okay, so our object, if this is 34, then the object would be basically over here. Okay. And now let's find the height. That's the part that didn't make sense before. HI. So we have minus DI. Okay, we want to find the height of the object. So we got to flip that over. So that'd be minus HI times DO over DI. That'd be minus 34 centimeters times DO, which is 120 centimeters, divided by DI, which is minus 24 centimeters. Just plug that in. So I'm getting 170 centimeters. which is 1.7 meters, which is a reason. Let's convert that to inches just to, let's say we have 170 centimeters. I'll put it here. 1 inch is 2.54 centimeters. So 66.9 inches, so about 5'7". So yeah, perfectly reasonable height for someone to be. So the other one, it was smaller than this number. So I don't remember what the number was, but yeah, sign convention you have to be very careful about. But the actual convention I wrote down doesn't actually cover this case. It just says image distance. It only tells you what to do if the object is real. And if you have a virtual object, it doesn't actually tell you in the sign convention. So, but the example in the book does talk about that. But I think it's best just to look at it, it's a lens, light can go in either direction. You look at it the other way. So if these two are in the same, if the image and object are on the same side, then DI is negative. Okay, so that problem now makes sense. I kind of tried drawing a ray diagram for this one, but yeah, maybe I'll look at that again. Yeah, I guess if we know where the object is, let's see if we can draw that. I'll just draw it separately. Okay, so here our object is 120. So let's say here's 120. So each of these tick marks is 30, so we'd have a focal point here and here. See if this works. If we just consider an object with light going this way. So that'd be one, and the other we have, we're going towards a focal point and then trace the light backwards. So somewhere around here. That's a little more reasonable. I mean, the image would kind of be over here between 0 and 30. Looks like it should be a little closer to 30 than the drawing indicates, but close enough. Yeah, a ray diagram doesn't help too much because in this case, it's only useful for checking because we can't draw it until we know where the object is. So again, have to be careful using the sign convention. And I'll make sure not to put something like this on the test because our lens convention doesn't cover this specific case. Guess I don't want to write too much about that. But yeah, I guess that's it for this question.